We've seen that finding the force on charges and also taking charges and finding the electric field can be a bit complicated at times, especially when we've got a continuous charge distribution like that semicircle where we were trying to find the electric field and we only found it in one spot. And so what we want to do now is to develop a different way of finding the electric field. And this different way of doing it is called Gauss's law, and it involves defining a couple of things in order to do that. First, we need to describe the flux. That's an important concept, and so this is eventually heading back to our goal, so flux, and then from that we'll find the electric field. Right? And then from the electric field, we find the force, because force on anything would be charge times electric field. Okay, so that's where we're heading. We're going to spend most of this video talking about the flux, how it connects to electric field and electric field lines, and then from there, how it connects to this thing called Gauss's law. Okay, so the idea of a flux I need to introduce is really about a flow, often like a river flow, across some area. It's a measurement of something moving across an area. So in this case, it's not something moving, it's just a measurement of how much field. So here are electric field lines. Okay, so for a uniform field where the field is the same value at every point and it all points in that direction, and we can talk about the electric field that goes across, say, an area like this. Okay, and so we can say the electric field, here's my area, this plate, this square, the electric field going across this area, we measure the flux, in this case, as the electric field times the area. This is the electric flux, and that's the Greek letter phi. So the electric flux, let's first look at the units of this because it can feel like I have no idea, and knowing the units doesn't necessarily help us, but at least we have some idea of what it should look like. So the units of electric field, I can come back over here, since force is equal to charge times electric field, the units of electric field are newtons per coulomb, and of course then times area, which would be meter squared, or the flux would be newton meters squared per coulomb. Okay, so what does it mean? Well, before we get too far down the road of what it means, let me point out that I can take this same electric field that points like this, and instead of having my sheet of paper, for example, in this direction, I can take my sheet of paper and put it edge on. Okay, so here's my sheet of paper sort of like this. Now the flux is equal to 0 because there's no electric field going through the paper. So you can think of it as electric field going through the paper. So now I have to deal with the orientation. You can imagine if my sheet of paper, instead of straight like this, is sort of tilted at an angle, then I would be looking at a component of the electric field that would go sort of right through this A. And so taking those two ideas into account, what we do is we first say for a constant area and constant electric field, where these orientations are the same, we can say the flux is equal to E dot A. Okay, I don't know if you remember a dot product, and I've got this A, which all of a sudden became a vector. So first I need to define area as a vector, and then let's remind ourselves of how the dot product works. So A as a vector, well, A as a vector means it's got a magnitude, which is going to be the area, and then it's got a direction, and the direction is going to be given by the normal. Okay, so how do we find a normal? Well, when we introduced the idea of a normal force, we said it was perpendicular to the surface. So if my paper is like this, then my n hat, or my area, is in that direction. So this is kind of a weird one. So this would be the direction of A, or in hat if you prefer. So let's think about that with a dot product. The dot product, E dot A, is going to be the magnitude of E times the magnitude of this new vector I've designed, times the cosine of the angle between them. Okay, so the angle between these up here, that would be a phi of 0, because A, or this in hat right here, that's the direction of A, points in the same direction as the electric field. So let's check up here. Cosine of 0 is equal to 1. So E times A, E dot A does in fact give me E times A. This is 90 degrees. So this is an angle of this angle between them. Notice this angle between them is different than what I'm calling the flux. I know we got Greek letters flying around everywhere. That's 90 degrees. Cosine of 90 is equal to 0. So in fact, this dot product is going to capture these things. So if I do, in fact, sort of something with, I've got an electric field. Again, this is all for a constant electric field. We'll deal with a changing electric field in a minute, or a spatially varying field. And I've got my paper sort of at an angle like this. Okay, so there's my paper. That shows up basically as the same thing. Let's do this. There's my paper as a surface, so it's going into and out of the screen, just so I can show the area here. Notice that would be the direction of my area vector. And so the angle between these two would then be this phi right there. And so my flux, which is a capital phi, sorry, I'll make it capital here, is equal to the magnitude of A times the magnitude of E times magnitude of A times the cosine of this angle. And this cosine, if this is 40 degrees, then that would be cosine of 40 degrees. And what that would do is pick up the amount of this area that's capturing these field lines, if you like. Okay, now in general, with non-flat surfaces, so when my paper is like this, figuring out the direction of the area is pretty easy. But just in general, if you have a surface that's curved, for example, then what you can do to find the normal of the surface is take your hand, doesn't matter left or right hand, put the palm on the surface and your thumb points in the direction of the normal. It's always perpendicular. So when I'm looking at the screen, when I'm looking at this surface, that gives me the direction of the normal. When it's flat like this, I've got the direction of the normal. Now, obviously, with this as flat, I can actually have it going up or down. And with Gauss's law, we're actually going to look at the flux through a closed surface. So you don't have to worry. Once it's closed, it's always pointing outwards is our normal. Okay, so that's the definition of our flux. The one thing I haven't addressed is, suppose in this situation, instead of having this electric field being nice, even lines, we have a situation. Suppose we have a situation like this, where the electric field is weaker and then gets stronger across the area. Well, clearly this is not anymore going to be just E as a constant times A. The dot product still happens, but instead what we would have, we would say the flux is equal to the integral of E dot dA. In other words, up here the flux is less, down here the flux is more, because we have a smaller area up here than we have down here. So the electric field is varying. So E times the little bit of area, maybe this top part of the area, times this electric field is going to be different than the area times this electric field and the area times this electric field. So this is our true expression of the electric field. We still have the dot product. We just have to take the electric field times a small amount of the area. So this is true when we have constant E and A. The more general expression is flux is equal to the integral of E dot dA. Okay, so far we haven't seen where this is at all useful and what this has to do with actually finding the electric field. So this doesn't look like it helps us find the electric field. In fact, all we've done is talk about if we have the electric field, we do this integral to find this magical flux for reasons that we don't understand yet. Okay, so the sort of the end information here is we're going to do everything we can to avoid actually doing this integral, because we're going to use it to find the electric field down the line. Okay, that's what Gauss's law is going to have us do. But we've at least filled in this first part, and my hope is you have some sense of a flux that is sort of accounting, if you like, of field lines or a strength of field going across a surface. Okay, so here's what I'm going to do to develop this idea of how we find the electric field. Suppose we have a positive charge here, plus Q, and it's just out in space. We know the electric field from this charge. And what we're going to do is ask, what is the flux, and therefore what is the electric field in a sphere around this charge? So here's, ooh, that's my lovely sphere. Okay, there we go. So this is a sphere of radius r. Okay, and let's draw the electric field lines. So drawing the electric field lines means we have field lines that go out like this, right, in all directions, goes along like that, and into and out of the page. They radiate out spherically, okay? So they point across the page. So if we look at this, the electric field lines are pointing in this direction for this sphere that I've drawn. So we've drawn a sphere of radius r. And so if I look at the area, so the area vector, notice this is going to change along the surface of the sphere. Like right here, if I put my thumb on that surface, then that's the direction of the area there. If I'm right here, that's the direction of the area here. And here, the area points like that. Here, the area points like that. The little bit of area, right? Because the whole entire area kind of doesn't make sense. So this is a little bit of area that points in this direction. For those of you who want to see it drawn out, you can draw it as a little tiny square, curved square on the surface of this sphere. For those of you who don't want to draw it up, that's fine. So that's your little dA, and we find the direction. And I hope you notice that dA and my electric field point at the same direction. Doesn't matter where I am. If I'm right here, E points that way, and so does my little bit of area. So this E dot dA just becomes E times dA times the cosine of the angle between them. Well, the cosine of the angle between them is 0. Cosine of 0 degrees is equal to 1. So that's just E dA. Okay, so and we can say that, in fact, once we've done that, we can actually say, well, the electric field is constant in value. So this is constant. And so then I can just turn this into E, I mean, it's constant around the sphere, E times A. And so I want to find this because I want to find the flux, even though I haven't told you why. There is a reason. We'll get there. Just have to hang with me here. So the flux for this situation is equal to the electric field times the area. Now the electric field for a point charge is just K times that charge, Q, over R squared. R is our distance to wherever we wanted to find the electric field. So say we're looking for the electric field right here on the surface, or right here, or right here, right? It points in different directions, but the magnitude is equal to this, right? This is the magnitude of E times the magnitude of this A, because we already got rid of the vectors by doing the dot product. It gives us a scalar. The area, now we need the area of a sphere. Now that's something you probably don't know, but it turns out that the surface area of the sphere, you can get this, you may have done this in calculus. The surface area of the sphere turns out to be 4 pi r squared, right? Pi r squared is the surface area of a circle, but if you have a sphere, then you have to multiply by this what's called solid angle here, and so that gives you this 4 pi r squared. And notice something interesting that happens. These r's go away, and so the flux is just K times 4 pi times Q. And K, you know K is 9 times 10 to the 9th, right? But there was another way we could write K, and we wrote it like this. We said K is equal to 1 over 4 pi epsilon naught. This is why we use this, right? If we plug that in here, what we get is the flux is equal to Q over epsilon naught. So here's what we get, and this is really Gauss's law, is that the flux through a surface is equal to however much charge is inside, enclosed or inside, over this constant, epsilon naught. And just as a reminder, epsilon naught is equal to 8.85 times 10 to the minus 12. Its units are 1 over the units of K, so that would be, let's see, newtons, coulombs squared, meters squared. Okay? So here's the thing. The flux, and hopefully this makes some sense, is a way to measure if there's a charge inside or not. So if I draw a surface like a square just outside here. Okay, so I'm going to make it a box. What that says is if there's not any charge inside this box, if this box is empty, it can have electric field lines going through it. So it does have electric field lines going through it. But what happens is those electric field lines are such that the flux, the flow, is 0 across the surfaces. Let's see if we can make some sense out of that. I'm going to go down over here and say I have, let's do a simple case where the electric field is just a nice constant going up like this, and I'm going to line my box up in a way that makes things a little easier. Okay. I realize this is not the same geometry as what you saw, but I want to point out that on the sides here, E and A, so this is the direction of A on a side, right? So on the sides, E dot A is equal to 0 because I have 90 degrees between the electric field and the area. So the electric field points up, the area points out, and so that's 90 degrees, and cosine of 90 degrees equals 0. So the flux through the outer surfaces is 0, which you could just say because you're like, the arrows don't go through the surface. It's only at the top and the bottom. But notice that at the top, we have the flux through the top is equal to E times A times cosine of 0 degrees But at the bottom, flux is equal to E a cosine of 180 degrees, and cosine of 180 degrees is -1. Cosine of 0 is 1. So the flux through the top is equal in magnitude to the flux in the bottom, but that's negative because the electric field points this way and the area points this way. So if we measure the flux through this entire surface, the flux through this surface right here, the flux through the whole surface is equal to 0, which there's no charge inside. So that holds here. The geometry is a little different, but here, because Q inside, Q enclosed is equal to 0, the flux is equal to 0. And this is really Gauss's law, even though it still doesn't feel like it's going to get us anything. Gauss's law says that the flux inside is equal to just the number of charges that are inside, the sum of all of them, divided by epsilon naught. So you could have a situation where you have a plus Q and a minus Q, and you could build some kind of a box around it, and the flux is equal to 0. You don't have to do the integral. First time we've avoided the integral is to just say, let's add up these charges that are inside the surface. So we can avoid our integral by just counting up the charges. But we don't use Gauss's law for that very often. Sometimes we're interested in what is the flux, and we count up the charges. What we're more interested in is using this to find the electric field, okay? So all of this is sort of a preamble to get you used to this concept. This is a very foreign concept that you haven't seen before. Don't be scared by it. We're going to use it a good deal so you can get a feel for it. But the key here is that the flux is equal to the charge enclosed of whatever surface you draw, and we can calculate the flux using this equation, okay? So this equation allows us to calculate the flux. This is another way to get at the flux. And so we're going to equate these two as a way to actually find out the electric field. So we're going to say this integral equals this. We're going to use it to find the electric field, and we're going to do everything we can to avoid doing the actual integral. We're going to set it up and then make some arguments about how we can avoid doing the integral.